So now, given that we have b a real number bigger than 0 and different from 1, the derivative of b of x is going to be the same exponential function b of x, but now multiplied by the log of b. Notice that when b is bigger than 1, we're going to have a situation where the log of b is going to be bigger than 0. And so the graph of y equals b to the x is going to have tangent lines with positive slopes for all x. And when b is between 0 and 1, the log of b is going to be less than 0, and the graph of y equals b to the x is going to have tangent lines with negative slope. So as you can see here, dependent of the base, if it's bigger than 1, like in this case, we have positive and increasing the slopes. And if we have numbers between 0 and 1, for example, 1/2 of x, 1/2 to the x, then we have negative slopes. In both scenarios, however, that is going to be governed by the sign of the log. Since if we have a number between 0 and 1, the log of b is going to be negative, and if we have a number bigger than 1, the log is going to be positive. So that's what is pretty much flipping how the tangent lines behave. Now let's take a look at some examples of calculating derivative with the exponential functions. And we're going to have certain exponentials, and we're going to play in the same way with the trigonometric functions, the product rule, and so on. So the first one is going to be y equals 3x. B is going to be y equals 1082 to the t over 12. C is going to be e to the secant of x. And D is going to be log of x squared times phi x squared. Okay. Now the first one follows exactly the rule that that we described. So y is equals 3 to the x, so y prime is going to be the same thing but multiplied by the log, the natural log of 3. Okay, so not a lot to do in there. B is a little bit more involved since we have a bigger base. We have 1082 power to t over 12. There's a small chain rule here going on, but essentially y prime is going to be the same thing. This is the base, 1082 times t over 12, and we need to multiply by this chain rule, so 1 over 12, but we also need to multiply by the log of the base, which is 1082. So at the end, this is going to be our solution for B. Now in C, we don't have anything special but a chain rule. We have y equals secant of e to the secant of x. So y prime is going to be, again, the same thing, e to the secant of x times the derivative of secant of x, which is going to be secant of x by tangent of x. So that's the chain rule. Yes, normally we need to do the log of the base, which is log of 1, log of e. But in this case, notice that log of e is just going to be 1. So essentially that's just going to disappear. So that's one of the only things that changes when we're using natural log in the Euler function. It gets to be a simplified version of the exponential formula. Now D is just a product rule, and so if y is equals log of x squared times phi x squared, I can go ahead and use properties of the log to transform this into log of x. Times phi x squared. And so in this way I simplify everything. This becomes 2 over x times phi x squared plus 2 log of x times 10x. Okay. Simplifying a little bit more, this is going to become 10x plus 20x log of x. Okay, and so that's for this first couple of examples of how to use the exponential derivative. Now we can use the exponential function in a lot of different models, and then that's going to be involved in logarithmic equations and exponential equations to find out certain results. One example of this is the following example. We have a table that shows how the incidence of Down syndromes in newborn infants increase with the age of the mother. So the data can be modeled with the exponential function p of a given by 1 over 1,613,000 times 1.2733 power to the a. So notice that our variable is the age, and we have this table that that says what is the incidence of Down syndrome depending of the mother, starting at 30 years old and around 49 years old. Okay, so now we have that this is 1 in 900, but we can really see that as a decimal 0.0111, and when we're getting more advanced, let's say at 49 years old, you can see that the decimal is 0.08333. Okay, now according to this model, at what age is the incidence of Down syndrome equals to 0.1? So that means 1 in 100. So we can try and look in the table, but we don't really have that information in here. Should be closer to 39 and 40, or maybe 40 and 42. So that gives me a guesstimate of where that's going to be. But to be precise, we can use this function and set it up to be equals to 1 over 100. So 0.01 equals to this, and find what the age is. So let's do that. Okay. Also, we can compute what is the rate of change of this and make an interpretation at the rate of change in 35 and 46 years old. Okay. So notice that if we plug the data in our model exponential, we can see that it has a very good fit of the data within the exponential function. And now if we solve for 0.1 for the first thing, we set up 0.1 to be equals the exponential function. Then we can multiply this constant on the other side and take logs on both sides. So now we're going to get that the log of 16,130 is equals to the log of 1.2733 power to the a. Using the properties of the log, I can get later that the a is going to be the quotient between these two log, and that's approximately going to be around 40, which means that around 40 years old, this is going to be around 1 in 100 for the incidence of Down syndrome. Now, if we're going to talk about interpretation, we of course need to find the derivative first. So this is a constant multiplied in exponential, so we only care about the exponential. This is an exponential with a base bigger than 1.27, but as a good derivative of the exponential is just going to be itself multiplied by the log of the base. Now, once that we have that, we can approximate this to another exponential multiplied by a different constant. And what this means is that it's going to measure the rate of change of incidence with respect to age. Okay, so for example, for the 35 years old woman, this is going to be the derivative of this function around 35 is going to be 0.007, which means that the incidence increases at a rate of 0.007 per year. By the age of 46, the rate of change is increasing significantly more, to a rate of change of almost 0.01 per year. So this is telling me how much is the danger increasing per year.